So as you can see today, I have notes for hash tables, and I'm going to run over these. And it's a summary of what's in the book. One semester, I decided I'd rather type them up instead of see my handwritten notes. So I typed them because there's quite a few. But we'll go through these, and we're going to talk something about a hash table. Now, y'all started working on your Big O notation. And one of the things we need to talk about is a due date for that. And that's something we'll set. I'll do a poll or something, and we'll pick a due date for that. But all of a sudden, you see something. We start talking about Big O notation, and I see a linear search has Big O notation of n. That means there's going to be n comparisons. That means my worst case scenario is I'd have to look at everything in the list in order to find the number. The number may not be there because the list isn't sorted. We have to go all the way through, or it is sorted and we still have to go all the way through. But it's a Big O sub n because I'd have to look at every single one. Okay. We know in a binary search, all of a sudden we have some kind of exponential going here where I'm taking it and I keep cutting it in half and cutting it in half, and I bring this whole log base 2 of n into play. And that's the way to represent going through and cutting it in half each time. So again, if I had 32, which is 2 to the 2, 4, 8, 16, 32nd power, log base 2 of 32 equals 5. And my worst case scenario would be 5 comparisons. Okay, and we mentioned a term about an unbalanced tree, how that would come into play if instead of doing, with the binary search, the worst case scenario would be a tree that goes dot, 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 all the way down the right. And then that would be O sub n because I'd have to take a look at every one. But for a balanced tree, or when we were dealing with a sorted array, same kind of thing, this Big O notation would be log base 2 of n. So if you started looking at it, great, you have an idea what I'm talking about. If not, it is what it is. But we're going to start taking a look at some faster ways to do searching to see if a number is in a list and so on. And today we're going to talk about a method called hashing. And this is one that will be a really quick, hopefully, quick way to go and check an array, see if the number's there or not. It won't be looking at every one. It won't be this cutting it in half method. It's another method in order to see if something is in a location or to go to a location and find out information. Because remember, it's not necessarily always going to be a number stored in a spot. It could be a struct. It could be a whole bunch of information. So we might want to find all the data that would be stored there. Okay? So what do we have? Definition of a hash function. Hash function is one that's going to be applied to a key field, which will give me a location, and finds out where that is in the hash table. Okay, so I have this whole key field. Now, what is the key field? Well, that's just part of the information being stored there. Just like the program I had you work on where you were creating a node that had 2 things in the node and 2 pointers, a left pointer and a right pointer. That was the last program you were working on. Okay, so the ideal circumstance, time required to locate an item in the table is Big O sub 1, which means as soon as I look, it's there. And that would be ideal for searching. Okay, so I'm going to start by saying I want to take a look at 31 unique numbers, one for each day of the month, in an array with the range from 0 to 999 to be stored. So I want to find, I have 31 unique numbers. They're in the range from 0 to 999. I'd like to know if they're stored. So what could I do? I could simply do something along the lines of this. I'm going to create an array of 0 to 999. Array of 1,000 numbers. In that array, the first number I want to store is 8. What's a great function? Well, f of x equals x. So if I want 8, I'm going to store 8 and 8. If I want 997, I'm going to store it here. If I'm going to want 2, I'm going to store it here. If I want 5, I'll store it there. Now, what if I said, okay, is the number 8 in this list? Well, the function you used was a direct one-to-one function. I'd go to 8 and say, yep, there it is. Whoop, there it is, okay? And I found it. Faster retrieval. But what's the problem here? The problem is I have 31 unique numbers in the range from 0 to 999. Tell me a little bit more about this array.
Is it limited?
It's not. No, it's not limited. But what's going to be the problem? You know, I store
It's not
997.
sorted.
What's that?
It's not sorted.
Then it doesn't necessarily need to be sorted, because I'm going to store 997 right in 997. I'm going to store 2 right in 2. So if I said to you, I'm going to fill this array with 31 unique numbers, and I want to know, was 5 one of the numbers I stored? You'd go to the array, you'd go to location 5 and look and say, yep, I stored 5. That's one of the numbers I stored, okay? Just like 8 was, just like 2, just like 997. But what's the problem when I'm done storing 31 numbers?
Wouldn't you have like a lot of wasted space?
I have a lot of wasted space. In fact, how much wasted space would I have here? What percentage of it is wasted?
99, 98, something like that.
How about 97%? So if I store 31 numbers out of 1,000, I'm wasting 96.9% of that. So what I need to do with this whole idea of hash functions, instead of having this one-to-oneness, I need to cut my memory down. Okay, I'm only storing 31 numbers, and I need to figure out a way to store the 31 numbers in this array so that when I go to look for them, I don't have worst case scenario, this number of comparisons, or big O notation, log base 2 of n searches to see if it's in there. So again, the idea is to be able to store information so that I can find it quickly. All right, so what I'm going to do is I'm now going to do something along the lines of, all right, so before I started on this last one, I wanted to go and say, all right, I'm going to take this table and what should I put in it to start to make sure a number's not in there? So when I initialized this array originally, what kind of number would I store in there? Since this is an array of integers, that what's in there? If you look real close, because why not fill it with negative ones? Negative 1, negative 1, negative 1, negative 1, negative 1. So if I said, is 3 in there? You'd go look and say, oh, it's not 3, it's negative 1. Gone, it's not, there's nothing there. And remember, this 5 could be a key field. Like I could say, is 5 the key field for the name Galen Han Mountjoy, right? I could be in this location storing an entire struct. Part of the struct might be the 5 that gets me to that location. Okay, so if I fill it all with negative 1s, then I kind of know when I get there, it's going to be empty because my information isn't stored. All right, so my next thought is, well, what if I cut this array down from 1,000 to how many numbers would I like to store? Well, I think I have 31 numbers, right? So instead of maxing out at all of this, what if I wanted to store the numbers in an array from size 0 to 30? Okay, my first number was 8. Cha-cha. 8 will go in there pretty nice, right? My next number is 997. I don't have a place to put 997. Any ideas where you'd like to put 997?
At the end, maybe.
At the end? Okay, I mean, that's possible. If I have 31 spots available in here, and I give you a big number, 58, How can I represent that as a number from 0 to 30? I give you, go ahead.
Could I mod it by 30?
Yeah, you can mod it. And this time I'm going to use a hash function of f of x equals x mod 31. So now if I said 997 mod 31, what does that equal? Oh crap, I get the times 3 is 93. That leaves me with 67, and times 2 is 62. I think I get the number what?
5.
5, right? So here was 8, 7, 6, here's 5. So now I'm going to store 997 in location 5. So now when I go to say, oh, is 997 in my list, we're going to remember what the hash function was, mod it with 31 and say, ooh, check location 5. Okay, check location 5. We go up to location in 5 and whoop, there it is. Okay, my next number I wanted to put in there was 2, 0, 1, 2 mod 31. Yeah, I'm going to put 2 in 2. Another number I had was, my next number I had in my list down here was 5. If I do 5 mod 31, what do I get?
5.
I get 5. So I go to 5 now, and what's my problem?
There's
I can't
something.
put it there, right? What do I have? Well, what I have is a collision. New term of the day. What I have there is a collision. Okay, so now what can I do with 5? Well, I need to go and probe through here and find a place to put 5. So I'm going to say, okay, let's go to 5. I can't put it in. I'm going to do linear programming, which means I'm going to move 1 to the right and say, ooh, that's empty. Spot 6 is empty. How did I know it was empty? Because what's in here? What should I have initialized this entire list to
-1.
start?
-1.
Yeah, -1. So I look and say, oh, there's a -1 in there. I'm going to put 5 there. Okay. So all of these other ones should have -1s in them. All right. So I start filling my list, and all of a sudden I say, uh-oh, I want to know if 5 is in the list. So I use my hash function, mod 31. I go up to 5 and say, crap, it's not in the list. Do I give up? No. I say, wait a minute, it's not in the list, but this guy also is not empty. And him not being empty says, okay, how did I do my probing? I went linear to the right one, and I go to the right and say, hey, 5 is here. I'm happy. It's in there. Okay. I didn't have to search through everything. I didn't have that log base 2 event. So it's a quicker way to do storage and retrieval. All right. What if I, so I just looked for 5. Now I'm going to say, what if I look for the number 36? What is 36 mod 5? Excuse me. I'm sorry. Mod 31. Oh, I was doing so good. Perfect. Mod 31. That's a real tricky question now, isn't it?
It's 1.
It's going to be 5, right?
Oh.
Not integer division, the remainder. Remainder's 5. Okay, I want to see if 36 is in the list. So I mod it. I go to location 5. It's not there, but I didn't give up. So I'm going to go to the right. Is this 36? Nope. Keep going to the right. Is this, time to give up, right? Because as I move through, I'm going, it's not there, not found. Okay. Not too bad. I can store it and I can retrieve it. Now, how many numbers did I say I wanted to store in this list? When I first started, I said 31 unique integers in a range from 0 to 999 to be stored in a hash table. Okay? Start by, okay. So, when I get into here, how many numbers am I filling this up with?
30.
31, right? Which means I'm not wasting any memory, am I?
Nope.
Nope. But what happens if I put the last number in and it has a modulus 5 and everything else is filled? In fact, when I get to the end, it wraps around because we're working with modulus, and I get all the way to here, and 4 was the last empty location, or that was the location of that number. Well, what is my worst case scenario in searching? Going back to big O notation, it's going to fall on that O sub n again. My worst case is I had to go through the entire list. That's not what I wanted. So now I looked at an array that was way too big. I looked at an array that's definitely too tight because my worst case is O sub n. So now I need to figure out an array size that's going to work well for storing these 31 numbers. Okay, so one of the things I'm going to do is say, all right, so I had trouble with an array, and let's go through and make sure we did everything we wanted to. Use a table of size 31. Okay, so we're modding with 31. For example, if I said 64, mod it with 31, I would put in the 2. Where would 128, 620, so we took care of that. And what if we run out of room? Well, again, that defeats the whole purpose because our purpose was to have faster searching in this. Okay, so what happens if I landed? I said we have ourselves a collision where values may end up at the same location. And what we do is something called linear programming. Go to the next location and keep moving to the right. That's what's called a probe sequence. And we would keep going until either the number was found or the array location was -1. Oh man, if I start coding this, I'm thinking collisions until a while, you know, all of a sudden I'm making some notes, not found, which is the -1 idea, or it was found kind of idea. So while it's not found or negative, so I could start making notes for later if I have to program this. As I'm learning this and talking about it, I wanted to see if 36 was there. I went to the location. It wasn't a match, but it also wasn't a -1. So I want to keep going until it's found or I reach a -1. So while not found or whatever that array subscript is not equal to -1 kind of deal. Talking my way through it using these logical operators and my relational operators. Okay, so I have all these collisions and now I'm saying, hey, I can do some linear programming and start moving to the right. Works fantastic. I hope there's more. Yes, there is. Not on that page. By the way, on Thursday, we will be doing a group project, and next Tuesday will be the test. Okay, so there are cases in searching to consider. If the location is empty, the value is not in the table, I would be done. If the location finds a value that we wanted, we're done. If another value is in that, we do this circular linear search until the value is found, which means we keep moving across that array. If I still haven't found it or I haven't found the -1, I loop around to the beginning and keep going. Okay? Well, again, we get into a problem when the table is full. Why? Because now we're on this big O sub n notation. And yeah, we might, okay. All right, well, my next thing is, what if I come back to my list and I say, all right, so we know our basic operations are insert, or basic functions include insert, what we would call traverse or search to go through. But now what happens if I wanted to delete a number? Okay, again, I'm working with this hash table. I want to delete a number. And what if I want to delete 8? I get to 8 and I say, oh, there's something there. I delete it. What would I put in there instead?
-1.
-1, good. What if I say, oh, I'd like to delete 997? I would go there. And what would I put in place of 997? -1, right? That's what we just said a moment ago. What if I now said, ooh, I went up here and I changed this to a -1. Now I say, oh, I'd like to see if 5 is in my list. So I do the hash function. I go up to 5. What do I see? A -1, which means, nope, it's not in the list. I'm done. Okay. Let's see if I can fix that. So when I deleted the 997, I put in a -1, which is one of my tripwires from up here when I'm searching, right? I have the function insert. I have the function search. Now I'm looking at delete. If I go back to search, I'm going until this -1, but this hits -1. I'm like, oh, crap. Should I give up? Yes or no? No, thank you, Conrad. No, I need another scheme. So if I'm going to delete something, what could I put in there instead of -1? Because remember, when I go back to my, go ahead.
Move down the 5s.
How about I do this instead? Put something else in there that says it's available, but not to give up on my searching. So if I'm going to delete, what could I put in there? Well, -1 is used. Tell me, Rashawn, hit me.
-2.
Excellent, -2. Because now my search will stay intact. I'll come in, the number 995 isn't there, but it also doesn't equal -1, which means I need to keep doing my probing to the right. Okay? So for my delete, again, I'm making notes. This was, that was a definition. This was when I was making some notes with insert. When I'm making some notes with delete, I'm going to use -2 so that I don't mess up my insert. Okay, good. And hopefully some of you saw when I put it up a moment ago, we're going to put -2 in. That way it'll be able to keep me going. All right, ways to improve performance. Increase the table size. Instead of having an array of 1,000 to store 31 numbers, an array of 31 to store 31 numbers, we're going to come down here, and studies have shown that we'd like to have a table size of 1.5 to 2 times the number stored. So if I said I want to store 31 numbers, what might be a range of numbers for 31? Well, let's see. If I have 31, 1.5 to 2 times the size, I'm looking anywhere from like 46 to 62 kind of idea. But when I'm doing some of this modulus and other work, I'm going to get myself into trouble where I may skip array locations. So when I start with the 31, I pick a range. One of the things I want to do in this range is pick a prime number so that I don't skip any array locations. So what might be a better size for this array? It rhymes with nifty T.
53.
Yeah, I think 53 would be a really good one. Yeah, I'm looking at 55's a no, 57's a no. Another option might be 59. Okay, we're looking at prime numbers. So I might use an array of size 53 to 59. Okay. Collisions. Use a different strategy for a collision. And if we remember right, a collision was when I put a number in and something was already there. So we looked at this linear and it was okay. But another one that exists is quadratic probing, where I may go 1 to the right, 1 to the left. Then I might go 4 to the right, 4 to the left, some kind of different programming, because I want to avoid this idea of clustering. That's where all the numbers get tangled up in one big bunch. Okay, so I could have different types of probing. So I'd like to use a different strategy to resolve collisions. So maybe doing a different probing, or I could possibly do a second hash function. Like after I mod it with 31, I can maybe do another function like 17 minus, x mod 17. All right. And finally, use a different hash function. What if I was storing letters? And I said, all right, I want to store the president's names. Well, how many presidents' last name starts with a Q? How many presidents' last name starts with a whatever? So I might want to change up my hash function and say, okay, what if it's more than just a single number? What if I said, okay, so I'm going to do this. I'm going to take the average of the first 2 letters of the last name and stick it in a location. Maybe that would be a better way to do it. So a different type of hash function, different than when I'm dealing with numbers I want to mod. When I'm dealing with something else, I might want to use a different hash function. In this one, I'm storing 31 numbers. Would I still mod 31, or would I be modding with my array size? So even though I'm storing 31 numbers, I'm going to use a table of size 53 or 59. And if I want to fill that, wouldn't I be modding with 53 so that I can have possible access at each one? So even though we're still at 31, we're not modding with 31 because I'd never get to locations 31 to 52. So I want to make sure my hash function is going to be the size of my array. And again, that's why we want to make it a prime number so that I can get in there and hit all of those. All right, so this guy right here, ways to improve performance. What a great test question that would be. You know what I'm saying? Okay, coming down, program. Here's what we have going. I first say do another example with numbers. Do you want to see another example? Or do you think you have the concept?
Another example.
You think you have the concept? Oh, I did hear another example. Okay, so I'm gonna take an array, and let's just do one of size 7. I want to store 8 numbers. I'm gonna do this in pencil. Example: store 8 numbers. Okay, and I want to store them. So how big of an array might I use?
$13.
13. Excellent. So now my hash function is going to be f of x equals x mod 13. So when I store them, I'm going to be able to hit those. So I want an array of size 13. I cut it in half, half, and a half. And that's what, that's 4, 5, 6, 7, 8. I need 5 more, 9, 10, 11, 12, 13. I'm going to do this and get rid of this. Okay, so now I have subscript 0, 2, 4, 6, 8, 10, and 12. Help me out. All right, give me a number I want to put in this hash function. I want to add, give me a number. All right, the range of numbers can be anywhere from 0 to 100.
25.
I'm sorry, say again?
25.
25. Where would 25 go? If I mod it with 13, where would 25 go?
2.
Nope.
12.
How many times does 13 go into 25? Once with a remainder of 12.
12.
Okay. Give me another number.
4.
4. That's easy. Thanks. Give me another number.
29.
29. Again, these are all negative ones. Where would 29 go?
3.
3. Give me another number.
3.
3. Where would 3 go?
5.
Yep. The 3 is going to go in here because at location 3, I already have the 29. And give me another number. I have a great one. How about this number? 38. Where does 38 go?
Would it go right before the 25?
Well, what was my probing? It was linear, which means I moved to the
Right.
Right.
right,
Sure.
and I'm going to put the 38 over here. Okay, so we filled the array with a bunch of numbers. All right, the next thing I'm going to do is I'm going to search. What number would I like to search for?
25.
25? It should be there. Give me another number to search for.
38.
The 38, good. So you've seen how my brain is working, and hopefully yours is as far as test data, because that's going to test the wraparound. Give me one more to search for.
3.
3, good. Now I'm going to delete. What number might I want to delete? 29? What other number might I want to delete?
38.
Not 38. I'm going to hold off on 38. I'm going to check. I'm going to delete this one. Okay, the 25. So now I'm going to do another search, right? And what would I like to search for? Well, if I deleted the 29, the reason I did it is I want to see if I can get over to the 3 and see if it's found, which it is. The other number I'd like to search for, now that I deleted the 25, I'd like to search for the 38. Okay, so if all of that works, I feel pretty good about my test data. Now, do I have clustering? Yeah, I have a little clustering there. There's 3 of the numbers. Do I have clustering? Yeah, I have clustering over there, the 25 and 38, but it's not too bad. My searches are still fairly simple. And that was 5 of the 8 numbers. Okay, so I'd still have 3 more numbers to put in somewhere depending on what's going on. So if you were to write a program for this, I kinda almost just wrote your demo. Do we like that demo? Is that a pretty good test demo? Say
Yep.
yes? Yes. So guess what? I want you to write this program and demonstrate what we talked about. The insert, the delete, and the search. The traverse could really just simply say print. You might want to have a print just to print out your array to make sure that it looks like what it's supposed to. You know, every time you add a number, display the array and see if it works. So that's 1, 2, 3, 4 functions and a main. Hopefully we have 10 people here. We can put you in groups of 5 to work on this program. All right. Again, insert, delete, search, and print. Insert, delete, search, and print or display, whatever you want to call it. Insert, delete, search, or print. Any questions? I think hash functions are kind of cool. I'm going to stop the recording.